Okay, folks. While I'm still working on the test so I can send it out to you, we'll continue with lecture notes. I won't go too far because chapter 14 is a little bit of a sticky wicket, but we'll see about it. See how far we're gonna get, and also I'll send you the test when I get it done, and then you can get started on that. But you'll have at least a week, if not more, to work on that test. So the longer I take to get it to you, the more time you have to practice some of the homework. I'll try to update the grade book at some point, but it'll get done when it get done. Let's go ahead and get started. Okay, let's get this. So, chapter 14. It's all about speed. About how fast can things go. So, now, previously in general chemistry, we learned about stoichiometry, the idea of you can predict how many products should form in a reaction based on looking at reactions mixing together. Oh, two of these react with one of these to form three products. But stoichiometry alone cannot predict the chemical's reaction rate, whether this reaction will take 10 seconds or 2 million years, the speed at which a reaction forms. So chemical kinetics is a measurement of the reaction rate. That's the main topic. Now, while we will not focus largely on these various factors too much, it's still very useful for us to know, and it's a perfectly good test question. But things that can affect the rate: physical state of the reactants, simply meaning the more surface area we have, the greater the mixing that can happen, the faster reaction can occur. All reactions in all states require atoms to collide. Gases are the easiest to react because they're constantly mixed and bouncing around on each other. Liquids, if you have a solution, they can react very quickly because they're pretty well mixed. But if you don't have two liquids that mix well, like you have oil and water, you really have to stir it up, or else you literally have that they only react where the two layers touch. And so you can have a slow reaction. If you have solids, they can still react, but you have to make sure to mix them up real well so that the solid surfaces rub against each other. But the nature of the reactants also matter. Is the reactant a stable one, or is it a unstable one, or unstable? Are the bonds particularly weak and reactive? So some things we'll learn when we talk about thermodynamics. It's endothermic to make this versus exothermic. Endothermic things, if you're making it, means it really doesn't want to be made. It wants to break apart. That's a very unstable product. Concentrations. This is the one we will focus largely on in this chapter because it's the one we have the most control of. The more reactants you have, oftentimes the faster they can mix and collide. You have a big concentration, you have it's going to react faster. If you're going to a party to pick up singles, and it's mostly married couples, you're going to have a hard time finding someone to date. But if it's a lot of single people, you will have a higher chance of finding a date. So it's all about the number of reactive atoms. We can also control temperature. We will focus on that near the end of the chapter. But generally speaking, the higher the temperature, the more energy the reactants have, and thus the faster reaction occurs, because it's all about collision and collision speeds. This is a hard, fast rule. It's not perfect, but it gives you a good grasp of most situations, where just about every 10 degrees Celsius you increase a temperature, the reaction speed approximately doubles. So if you increase by 20 degrees, you've quadrupled the speed at room temperature. A catalyst. If you have a catalyst, the catalyst will greatly speed up a reaction. We'll talk more about that later. But it all comes down to anything that increases the number of collisions will increase the rate. Large surface area, more collisions. Higher concentration, more collisions. Higher speed, more collisions. Catalyst just holds things together, allows them to collide better. But so rate. What is its units and how is it measured? A rate is going to be a ratio of some kind of amount versus some kind of time. The most common version is molarity, capital M, per second. Now you could do molarity per minute, molarity per day, molarity per hour, molarity per year. You could look at it as atoms. You could look at it as all sorts of things. But the most common one is molarity per second. Now, because it's a rate, it's just like a speed. So a speed would be like meters per second or kilometers per hour or something like that, miles per hour. But in physics, we have to give a dimensionality. You could be moving forward at a speed, but you could also move backwards at a speed, but that'll be negative. The speed, so in the same way, we can look at a speed of a product being formed or the speed of a reactant being consumed. Now, one is a negative rate, the other is a positive rate. Something increasing at a rate or something decreasing at a rate. So it's all about the direction something's going up versus down. Now, looking at a generalized reaction, 2A goes to B. In a simple reaction like this, the stoichiometry still holds true. For every time the reaction happens, 2A goes away and 1B gets formed. So looking at this graph, we can see the graph of A, in this case, starts initially at time 0 at 0.05 molar. Over time, it's decreasing, and it's decreasing at a rate that B is not quite at the same rate that B is increasing. A is asymptotically approaching concentration of 0, but it never quite getting there. B is going to increase to an asymptotically about 0.25 molar. Never quite getting there because it's unless it goes to 100%. But so it's B is increasing at half of the rate that A is decreasing. A is decreasing faster than B is increasing because it takes 2 moles of A to react and form 1 mole of B. So we can compare relative rates of two things together. We need to remember our Greek letters real quick. Greek letter delta. The capital triangle sign. The delta. Delta is used for a change. So the rate is looking at the change in the concentration of A over the change in time. like a rise over run, the slope. And we can compare them to the change in B over the change in time. And if we look, the relative slopes are A is a negative slope, and it's twice as fast. And so in order to compare them to each other, we need a negative 1/2. If you do that, the slope would be the same. The relative rates would be the same. Now take a new equation. A breaks apart into 1B and 2 molecules of C. So A decreases at the same rate that B increases. But C increases twice as fast as B increases because it produces 2 molecules of C. So if I compare the relative rates, A is the negative of B. One is a positive slope, one is a negative slope. But B is half as fast as C. So if C was, let's say, it's almost 0.04 for every 20 seconds, B would be almost 0.02 for every 20 seconds. A decreases by about 0.02 for every 20 seconds. And so we can get a relative rate comparison. This holds true regardless of how the thing breaks apart. This is universally true regardless of what we discuss next. That if I know the rate with respect to one component of a reaction, I can know the rate with respect to any other part of the reaction based on their stoichiometric ratios. Though for a generic reaction, little a, which is the coefficient of A, goes to little b of B. The ratios of their rates is simply an inverse of their coefficients. So if it's a 1-to-1 ratio, the rates are the same. The only difference is one is negative and one is positive. And so this means when we do a lab later, I can measure a concentration as relation to time by looking at like Beer-Lambert law. Beer's law says that I can relate the absorbance of light to a concentration based on a constant molar absorptivity and a constant path length. So if one atom, one molecule absorbs light, I can figure out the rate with regards to all of the parts. I can figure out all the other concentrations at any given time. But so looking at this in practice. So it doesn't matter what the chemical reaction is. For any amount of components, the relative rates are going to be equal to the inverse coefficients. So for a reaction, 5 manganese 4 oxides and 4 protons react in an oxidative fashion to form 3 manganese 2s ions, 2 permanganate ions, and 2 water molecules. Now, if the relative rate of consumption of manganese 4 oxide is 20 molar per hour, what is the rate of proton consumption? This is easy. So let me write this down real quick. We have 5A, 4B, gives us 3C, 2D, and 2E. And we say A is 20 per m per hour. And I want to know, what about B or C or D? So real quick, I'm going to go to go to the dochem. Okay. As you can see, I don't even bother to write the molecule. A is the relative rate of A is 20 molar per hour. So a generic rate, the generic rate is equal to negative 1 over little a of dA dt. That's going there. Well, the relative rate, negative 1/5 times negative 20 m over hours. So 20 divided by 5 is 4. So the generic rate of 4 m per hour. So if I want to know how many bees are being consumed under the same period of time, well, we're going to say negative 1/4 of delta H plus delta T. So to get this guy by itself, we're going to multiply both sides by negative 4. So how many hydrogen protons are being consumed per hour? 16 molar per hour are being consumed. What about the production of the Mn2+? Well, the rate is still, the relative rate is 4 m per hour. 1/3 of delta Mn2+ delta T. So once again, I cross multiply, in this case by 3. And so you'd get the production of 12 molar per hour of Mn2+. That's the rate of Mn2+. And finally, what about the rate of permanganate? Well, in this case, it's 2. So 1/2 delta MnO4 1- over delta T. Cross multiply, it'd be 8 m per hour of MnO4 1-. So if I know any one value, I can know the relative rates of all of the values. If I know any one concentration, I can know the relative concentrations of any of the other values relatively easily. So now, while we will not usually be measuring rates, we will. You can always take an average rate, but the average rate is somewhat inaccurate, especially depending on when you stop measuring it, because you're going to slowly approach the asymptote. So if you measure this over a long period of time, you're going to get a very low average. What's more useful is an instantaneous rate. An instantaneous rate is when we take the tangent to the curve, where a point where a slope only touches this curve one time. We'll often use this at the initial rate. We'll only really look at the how fast is it initially going, and not so much about when it starts to peter off. We prefer the initial rate to measure when the speed is the fastest. But there's where you get into calculus. While we won't need to do any actual calculus, I'm going to wave my hands for the most part. This is differential calculus at its best. You're measuring the change, the rate of change. Eventually we'll go on to write what's called a rate law. The rate law is a chemical equation that tells us a relationship of the reactant concentrations to the speed of a reaction. So even though the relative change in concentration of A and B is related to the stoichiometric ratios of the two, the dependence on the speed of the initial concentrations is not a stoichiometric relationship. So the generic rate is going to be equal to a constant K, which is called the reaction constant, times the concentration of a reactant A raised to a reaction order, times the concentration of B raised to a second different reaction order. The key here is that these reaction orders are going to be integer values, but they are not necessarily directly related to the stoichiometric coefficients. The larger the order is, the greater the effect of the concentration will be on the rate. You can get an overall reaction order by adding the two orders together. So looking at some experimental data right here. In the reaction of N2 plus H2 goes to ammonia. Now, the chemical reaction would be a ratio of 1 to 3. 1 to 3. One molecule of nitrogen reacts with 3 molecules of hydrogen to form 2 ammonia molecules. But as we see, when we have equal amounts of nitrogen and hydrogen, the rate is 3.5 molar per second. If I decrease the amount of nitrogen while leaving the concentration of hydrogen the same, the rate decreases. If I were to decrease the amount of hydrogen while leaving the amount of nitrogen the same, the rate stays the same. And if I change both of them, but we can see that, there is a direct correlation between the amount of nitrogen present and the rate, but there is not actually a correlation between the amount of hydrogen present. And that can only be determined experimentally through a rate law. We will do a lab based on this. So the key thing to remember is that the rate does not directly relate to a balanced chemical equation. It's actually going to be based on smaller equations that combine together. That's going to relate to what we're going to call the mechanism. But we'll have to get there later. But so because of that, because the overall balanced equation is not quite there, we will get reaction orders that typically fall into 3 different categories. First is a zero order. The reaction rate is independent of the reaction concentrations, meaning the amount of hydrogen, as long as it's not 0, did not affect the rate. A first order. The reaction rate is directly dependent on the reaction concentration. The speed decreases as the concentration decreases in a somewhat linear fashion. And then second order. The reaction rate changes by a squared factor with the reaction concentration. So if the concentration halves, the reaction rate is quartered. Now these orders and the rate constants can only be determined experimentally, and the easiest way to do that is by varying reaction concentration and then measuring the initial rate. How fast does it go? So to determine these orders, the rates of 2 reactions will be measured, where only one variable is allowed to change and thus be compared. So we're going to set a relationship between the two rates and the two rate laws. The brilliance being, since the orders will not change and the k's will not change, anything that is identical on top and bottom can be simplified. So, for example, if we only allow the concentration of A to change, B being the same cancels out. It is not affecting the rate. We can measure that. So we get that A to the n over A to the n. We can factor them in to the B into the n. So we look at how does the rate compare to the concentrations. So if I look at the rate of 3.5 or 1 over 1.4, you get a ratio of 2.5. If you get 0.5 divided by 2, 0.5 divided by 0.2, you get 2.5. What order of n would be such that 2.5 to that power equals 2.5? Sometimes you can just guess. Since it's only usually 0, 1, or 2, you can just guess. 0 order, any number raised to the 0th power is 1. Any number raised to the first power is itself. So 2.5 raised to the first power is 2.5. And then if this was a bigger number, they would try squaring it. But here's what happens when you have to do real numbers and it's not quite so pretty. There's a rule of logs. Log of a number raised to a power is the same as that power multiplied by that log. So in this case, you take the log of both sides, of both values. And so by comparing the relative logs of our two numbers, I can figure out what n is. So if n ended up being like 0.87 experimentally, then we could round it. 0.87 turns out being close to 1. So, but that's a case where you have to do experimental results. So we would repeat it again with a second trial, but this time we allow the other thing to change. So we look at how hydrogen affects the rate. Well, when hydrogen decreases by a factor of 2.5, but we compare 3.5 to 3.5, that gives you 1. So in this case, log of 1 is 0, so any number divided by 0 divided by any number is 0. M has to be 0 order. So that leaves us with a generic rate law. Rate is equal to a constant K times the amount of nitrogen times hydrogen raised to the 0th power. To get our K value, we will just plug in relative concentrations and solve for a K. So we have 2.1, and it doesn't matter. If you did this right, any value should work. 2.1 equals 0.3 times K. 2.1 divided by 0.3 is 7. Now, if I did 3.5 divided by 0.5, you get 7. 1.4 divided by 0.2, it's 7. So the idea is that if you've done this right, the K should be more or less the same, unless you have real and ugly data. The units of K represent the cancellation of the units of our A and B. So if a rate is in molar per second, and I'm dividing by a unit of molar, the molar cancels out, and I'm left with 1 over seconds. But it's all based on the units. So we will do a problem or two. So look, I'm going to have to write down these numbers real quick. 0.5, 0.5, 1.25. 0.3, 0.7, 0.5, 0.7, 0.3, 0.4. 2.45 and 0.48. I'm just writing those down so when I switch over to the dock cam, we can see this. Okay, looking at the dock cam. The first thing we need to do is compare which two experiments. If I compare this guy and this guy, I can figure out B, how B changes. If I compare this guy and this guy, I can figure out how A changes. So I'm going to start by comparing 1 and 3. So 2.45 m over s divided by 1.25 m over s equals generic k over generic k. 5 over 0.5. And we have 0.7 over 0.5. So just looking at that. These cancel out to give you 1. These cancel out to give you 1. So what we are left with is 2.45 divided by 1.25 is 1.96. 7 divided by 0.5 is 1.4. Okay. Those aren't quite. Now you could guess, but I'm going to do the log method. So log of 1.96 equals n log of 1.4. So we're going to do that real quick. Log 1.96 divided by log of 1.4 gives me n must equal 2. But I could have tried that. Said n squared, 1.4 squared is, 1.96. Hey! But that doesn't always get you the right answer. So I'm doing it the hard way. Okay. So we know n of 2. So now we're going to compare experiment 3 to experiment 2. 2.45 m per s over 1.47 m per s, k over k. Now it's 0.5 m over 0.2 m, 0.7 m over 0.7 m raised to the power of 2. Doesn't matter that's raised to the power of 2 because I have the same number. It goes 1. 1 squared is still 1. However, if these did not give us 1, because we now know this number is, we could figure out and solve for this and get that to the other side. There might be a case where you have to do that. It's annoying and a pain, but you could absolutely do that. So I get 1.67 equals 0.5 divided by 0.2. It's 2.5. I'm trying to figure out, did I write something down wrong? Let me see. Oh, yes, I did write something down wrong. That's actually 0.3. So I could have potentially compared this to this as well to get the same. So 0.3. So instead of 5 divided by 0.3, you get 1.67. So in this case, 1.67 equals 1.67 m. So m must equal 1. So my generic rate law is now rate is equal to k a to the first b to the second. So in order to solve for our k, we're going to plug in one of our values. We'll go ahead and plug in the bottom one because it's feeling lonely. 0.48 m over s is equal to k, which is 0.3 m times 0.4 m squared. So multiplying those together, so 0.3 times 0.4 times 0.4 gives us a value of, so we have on this side, k times 0.048. Now here's the trick. M times m times m is m cubed. So if I'm solving for k, I'm going to take 0.48 divided by 0.048. So I had to write up here 48 m over s times 1 over 0.048 m cubed. One of these m cubes cancels out. One of these m's cancels out. So we get units of 10 over 1 over m squared s. That's our k value. That's our k value. I know, sloppy, I know. That's me to a T. Sorry. So that is our setup. We will go ahead and stop there. I know we could absolutely go a little bit farther, but that seems like a good stopping point. We will not talk about differential and integrated rate laws. It's good enough to start with what's a generic rate law that we can determine experimentally. So, okay, have a good day. And look for the test in the next couple days if I don't get it to you today.